The problem statement from GATE Physics 2020 reads as follows. Which one of the following is a universal logic gate? We have been given 4 options. This is a multiple choice question with only one correct answer, and we need to find the correct option. Before we solve this problem, let's talk a bit about some concepts. So what do we mean by Boolean algebra? So Boolean algebra performs 3 primary operations. The first is conjunction. Conjunction means the output will be true only when all the inputs are true, and this is often denoted using the dot symbol or the multiply symbol. Disjunction means the output can be true if at least one of the inputs is true, and thus this is denoted by the plus symbol. Negation is whatever the input, it will be inverted. The input is high, the output will be low, and vice versa. So this is often denoted by bar, right? This is the bar symbol. All right. And the values that we use here are zeros and ones. So for instance, 0 times 0, so 0 is a value, so 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, 1 times 1 is 1. Similarly, 1 plus 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 again is 1, 1 plus 1 is 1. And there are 2 other laws called De Morgan's law. These are often used to convert to conjunction to a disjunction and vice versa. You can see this is converting a multiply to an addition, and with some using some negation. So solving the problems, we use these De Morgan's laws. The Boolean algebra is often implemented, the conjunction, disjunction, negation is implemented using something called the logic gates, which we see here. In the top row here, you can see the name of the gate, and these are the algebraic expression. I told you the bar is for negation. You see this dot is there, so this is multiplication or the conjunction. You see this plus, this is the disjunction, or these all called the or gate, and this is the conjunction, is also called the AND gate. You can see the symbols here. So for instance, NAND is interesting. It's nothing but the AND gate followed by an inverter. That's why you see this circle of the NOT gate here. What is a truth table? In the truth table, you list all the possible combination of inputs and you try to find the output, because we already know the algebraic expression. So for instance, let's talk about the very simple gate, NOT gate. So NOT gate has only one input. The possible combinations are 0 and 1. And this is an inverter, so it will be 0 bar, which is 1, and 1 bar, which is 0. So very simple truth table. AND gate has 2 inputs, A and B. So the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And X is nothing but A times B. So we know that 0 times 0 will be 0, 0 times 1 will be 0, 1 times 0 will be 0, and 1 times 1 will be 1. Similarly, you can do for OR gate and any other gate. The interesting thing is that the NAND gate, I told you, is AND followed by a NOT. So invert this 0, you'll get 1. Invert this 0, you'll get 1. Invert this 0, you'll get 1. Invert this one, you'll get 0. That's how we get the NAND gates. Key thing to note here is that AND gate cannot be used to perform the 3 primary operations. Note, I told you conjunction, disjunction, and negation. So these are the 3 primary functions. So AND cannot do that. AND can easily perform conjunction, but it cannot perform negation. There's no way it can invert a signal, right? Similarly, OR can perform a disjunction but cannot perform a negation. However, there are 2 gates, NAND and NOR, which can perform all these 3 functions depending on how the inputs are arranged, right? And hence these are called universal gates. So why they are called universal? Because they can perform the 3 primary functions on their own using 2, 3. Let's say using 3 NAND gates, you might be able to implement an OR gate or a NAND gate or an AND gate. So similarly, just by using one flavor of logic gates, you can get all the logic gates and all the primary operations. That's why they are called universal, right? So here is a NAND gate. So this is a NAND gate you see on the top left, and we have implemented an inverter. So I'll try to solve this. So we know that the truth table of an NAND gate looks like this. So A bar is the so A and A are the inputs. Note the 2 inputs are A and A, and let's say the output Y. What is the output? We'll see. So there are only 2 inputs possible. Either both are 0 or both are 1, because both are the same, and we know that Y equal to A times A whole bar, right? So 0 times 0 bar will be nothing but 1. Similarly, 1 dot 1 bar, which is 1 bar, which is 0. So what's happening? When the input is 0, the output is 1, and when the input is 1, the output is 0. This is nothing but a NOT gate. So when NAND gate is used in this configuration, which you see on the top right, you'll get an inverter. So we saw that just by using a NAND gate, we have created an inverter. Similarly, you can create any other gate or any other combination logic for that matter just by using the NAND gates. Similarly, you can create a NOT gate from a NOR gate, and you can see here we have used 3 NOR gates to create an AND gate, 4 NOR gates to create a NAND gate. So you can use any, but all of these are the same flavors. All of them are NOR. That's what we mean by universal gates. Getting back to the problem, it said that which one of the following is universal logic gate. So we saw the meaning of universal, right, in our discussion, and we saw there are 2 of them. There are NAND and the other is NOR. And this question is only one correct answer, and NAND is an option, so D is our answer. So that is all. Thank you for listening.